In our last lecture, we developed a matrix to describe the transition probabilities, and we talked about the probability of an atom transitioning from from an initial to a final state spontaneously, and producing that into a solid angle d omega. So we developed then through the dipole moment for the atom and how that was related to the final and the initial wave functions of that atom. And you may recall what those looked like, so I'll just bring them up here to see where they were. So we had that we defined R of I, which is related to the integrals of the wave functions and the position vector R. And that's related to the dipole moment. So we've now defined a dipole moment for our atom as it changes from its initial to its final state. It had with the two different wave functions associated with that. So miraculously, we are now finally at the place where we can relate that to Einstein's coefficients. And once we have Einstein's coefficients, we can then go backwards to some of the things that we talked about in week 5, where we related Einstein's coefficients to intensity, to mean intensity of emission, to absorption coefficients and emission coefficients. And that allows us to move forward with the entire process of radiative transfer as we have before. So here we are on the brink. Okay, so we can finally get to Einstein B coefficient. And in fact, it turns out that the semi-classical approach allows you to predict an Einstein B coefficient, but it doesn't allow you to predict an Einstein A coefficient. But fortunately, we know from detailed balance, which we developed back several weeks ago, we know how to derive, once you have one Einstein B coefficient or one Einstein coefficient fully, you can derive all of the others. So if you have the B1 to 2 state, then you can get the B2 to 1, or you can get the A to 1. So we can finally derive the Einstein B coefficient, which is related to the dipole moment very simply as the coefficient for the transition from the initial to final state is equal to 8 pi squared over 3 h bar squared c cubed times d f initial, where that is the dipole moment, the magnitude of that dipole moment. And this is a key result. So I'll put it in a box. So it tells us that the Einstein coefficient for the transition from an initial state to a final state is related to the wave functions of those two different states. So that's why we spent so much time in our previous set of lectures developing an understanding of the wave functions for atoms. You can imagine having a hydrogenic atom having a very simple wave function for an energy level of, say, n equals 3, and we could work on how it would look for a wave function transitioning, that it would transition to, say, an n equals 2 energy level, and that we could bring it together. So once we have the Einstein B coefficients, it's often helpful to write this in terms of oscillator strengths. An oscillator strength, we define the oscillator strength and that's probably a term that you've come across before. So we define the oscillator strength FIF, which is equal to 2/3 omega Fi over E squared m over h bar times the dipole, the magnitude of the dipole squared. And that relates to the Einstein B coefficient. You can just do the algebra to show that yourself. In the following way. So we can now write out Einstein coefficient BIF in terms of the oscillator strength for a particular transition. And it is common to define oscillator strengths for transitions to give them as numbers that you can then work through to come up with the Einstein coefficients. And you can write that also in terms of nu Fi. If you'd rather write that instead of the angular frequency, write it in terms of the frequency, MC, and the oscillator strength, Fi. So now I want you to recall how you can relate G, the statistical weight of a particular transition. So we can say G initial final, GI times BIF is equal to G final, the statistical weight of the final state. So that's how the many electrons, how often you would have electrons in that state. Oops, sorry, I should have written that in terms of final initial. So once we have BIF, we can derive BFI given statistical weights. And statistical weights we can relate to quantum numbers. So that's good. We actually have everything that we need to know there. And also that you can relate the Einstein coefficient AFI to 2 nu cubed over c squared So given our final determination based off of the dipole moment of two wave function states, we can relate the Einstein coefficient. One Einstein coefficient will allow us to derive all three Einstein coefficients. And so that means that I hope I have this the right way around, 2/3. I think I have that possibly backwards. Okay, so what we have is that in the situation where you have what's called a strong transition, F is on the order of 1. If F is equal to 1, it's a dipole transition. And not all transitions actually allow F to be equal to 1. And if F is equal to 0, it's what's called a forbidden transition. And in this case, when F is equal to 0, we have to include other forms of the dipole expansion. So we expanded that term, that exponential of I k dot r. We expanded that into a dipole plus a quadrupole plus an octupole term. If the dipole term comes out to be 0, that is, can happen depending upon what the two wave functions are for our initial and our final states. It may drive the dipole to be 0. In that case, the oscillator strength becomes 0. We have a forbidden transition. And in order to actually see emission from that transition, we have to consider the higher order terms. So this is exactly what happens for something like the hyperfine transition, which we have to include much higher order terms in order to get to it, or even just many different forbidden spectral lines. And we'll talk a little bit more about those in upcoming lectures. So our next step, now that we've actually gotten to the place of having Einstein A and B coefficients, which should allow us to derive emission coefficients and absorption coefficients, which are the key elements for understanding our radiative transfer. Now that we have those, we need to move on to understanding what transitions are allowed, which transitions are forbidden, and what are the rules that define those. And these are the so-called selection rules, and we'll pick that up in our next lecture.